Okay, hello. I wanted to get us back into this mindset of the different perspectives that we've seen in this course, the sort of the row perspective, the column perspective, the transformation perspective. And so I thought that it would be nice to start with some examples. Remember that pretty much everything we've seen so far comes down to the idea that the question of whether or not there's a pivot in every column or a pivot in every row of our given matrix. So if we start with this example right here, I want to start with an example where there's a pivot in every column and not every row. And so here's a matrix. It's 4 by 3, 4 rows by 3 columns. Here's a couple of vectors that live in R4. Notice the only difference between B and C is that I changed this 5 to a 6. Otherwise, they're the same vector. And if we think about the augmented matrices, right? So I want to take A and augment it either with B or with C. And then we row reduce. Right here, I'm going to start it in row reduce. And I did this in Mathematica. And if we row reduce A augmented with B, we get this reduced matrix. So notice I'm calling E the sort of the 4 by 3 matrix that you get. That's the row reduced type. Maybe E is for echelon. And it's the same E in both cases, whether I row reduce with augmented by B or by C. And I'm calling the new vector B prime and the new vector C prime just to give them names. But if you notice, this is kind of the different, I'm giving these two examples to illustrate the different scenarios, right? Because this ends up having 3 pivots, right? This, when we row reduce A, we get 3 pivots, 3 pivot columns, if you want to think of each column as being a pivot column. But in the first case, notice we get this nice row of zeros. We were 0 equals 0, basically. So remember, that's the nice consistent case, versus over in this other one, we get 0 equals 5, which is bad, right? That means all sorts of things go wrong. So let's talk about this from probably the most natural. The one we started with was the row perspective, right? So here's the row perspective. And it says that basically, if we want to think that the augmented system, that's really the equation AX equals B. And if we write out what that all means, that's just a system of 4 equations and 3 variables where the coefficients of x1, x2, and x3 are all the numbers here. Really, there's like a 1, 1, 1, 1, 1 there. If you think about ones being there, then you get the first column is 1, 1, 1, 1, 1, 2, 3, 4, 2, minus 1, minus 2, 1. And then there's B with the numbers after the equal sign, right? And so, that's how we think of a matrix. In the row perspective, we think of it as a system of equations. And when we row reduce, this basically, if we just read off, what we're looking at here, right? This says x1 equals 2. This one says x2 equals 1 and x3 equals minus 1. And so that's where this solution here is coming from. So this does have a solution you should check, by the way. It's not a bad idea to check. For example, like 2 plus 4 times 1 plus negative 1 is 2 plus 6 plus negative 1 does equal 5. So, this is a solution. But when we row reduce, if we change this number right here to a 6, so that we're row reducing AX equals C instead of AX equals B, then we get this inconsistency coming from the 0 equals the last row of the row reduced matrix, right? So that has no solution. Okay, so you guys are all comfortable with that. And so in one case, we get a solution, we get a unique solution. I should stress that. There's no free variables, right? Every column is a pivot column. So we get one and only one solution. And if we augment with C, we get an inconsistent system with no solutions. Okay. And so then that asks the question, begs the question maybe, what can we say about in general, if I wanted to change these numbers after the equal sign to be anything, if I wanted to change these to be any numbers, then that's this y right here. What could I say about such linear systems? And we've basically seen the two cases. So either, so ax equals y, I guess, either has a unique solution or no solutions at all. Right? For any, as we choose different y's, it's going to be one of those two cases, but you'll never have infinitely many solutions, for example, right? Ax equals 0 is worth thinking about because we say these homogeneous systems are always really important. If we think about ax equals 0, that's going to be, well, stop. Oh yeah, that's 0. That lets us think, that leads us to think about the augmented matrix A where you just augment it with a bunch of zeros. And if you augment with a bunch of zeros, right, you know that what's going to happen is nothing's going to happen to that column as you row reduce. So that's going to row reduce to just the same matrix with a 0 column. And so that means, really that means x equals 0. Right, that's the only way. So if ax is 0, then x is 0. So this only has the trivial solution. Okay. So that is, so we understand exactly what's going on with this, any system that we have using this coefficient matrix. All right, so that's all the row perspective. Now, if I wanted to move to the column perspective, well, think about what we have here. We have, if we want to think about the augmented system again, it's almost like I could, if you think about putting the like multiplying through the x1 and all here, and the x2 and so on, and then combining these into one big vector, you would basically recover the linear system that we saw. You would recover this linear system, right? So that's just equivalent. It's basically like, think about factoring the x1s out of this, and then you get times the vector 1, 1, 1, 1. Right? If you could like take the x1 out and so on. And so this is the same exact thing. It's just the same information, just presented kind of in terms of the columns to the rows. So we think of this as a vector equation, and it lives in R4 because each vector has 4 entries, right? And so we think of this as really looking at linear combinations of these 3 vectors. And I'm going to rename them just A1, A2, and A3. If, like the columns of the matrix, let's call them A1, A2, and A3. This was B. So this really just asks the question, is B a linear combination of the columns of capital A, right? Is B a linear combination? And that's kind of what that's what AX equals B turns into whenever we start looking at it from this perspective. But again, we already saw a solution, right? We saw the solution 2, 1, minus 1, because we've already row reduced. And so those are the values of the scalars that sit in front of the vectors. So in fact, you actually get this equation 2 times, if I basically plug in 2, 1, and minus 1 in for x1, x2, and x3, you should pause and check that if you actually do this, you actually get back the vector 1, 5, 7, 5. You get back the vector b. And so what that means is that yes, so the answer here is yes, it is. And remember, the other way that we say that is that we say that B lives in the span of A1, A2, and A3. That's another way. It's like we think of the span being as this the set of all linear combinations of the column vectors. And so B lives in that span because B can be written as a linear combination. Okay. Similarly, if we change this 5 right here to a 6, then that's the case where we've augmented with the vector C, and we saw that was inconsistent. So it's impossible. It's impossible to generate the vector C 1, 6, 7, 6 as a linear combination of these 3 columns. So C is not in the span of A1, A2, and A3. Okay. So let's think about, again, some general questions. If I think about, notice I put a Y here now. If we think about just sort of an arbitrary vector, if we want to look, if we want to think about, just what can be generated basically by these 3 vectors. What if we take every possible linear combination of the 3 columns of A, what can we possibly get? And we see we can't get everything, right? So we can say so from the example with C, from Y equals C, we know that the span of A1, A2, and A3 is not all of R4, right? It doesn't span everything because there are vectors not in the span. And we sort of expect that now, right? We've sort of gotten enough into dimension considerations to know that if we have 3 vectors, there's no way they can span all of 4-dimensional space. Just like 2 vectors in 3-dimensional space could only span a plane at most. 3 vectors in 4-dimensional space can't possibly fill up the linear combinations that can't possibly fill up all of 4-dimensional space. So that's an expected outcome. So, we could be a little more specific about what they span, but the point is it's something that's not all of R4. Now, if we ask, so that's the span question. If we ask about linear independence, well, linear independence comes down to the question of whether there's some way to write one of the vectors as a linear combination of the others. And we sort of turn that around to say, is there a way that we can pick non-zero coefficients to make this equation that I just wrote down true? That there's some way to find x1, x2, and x3 so that the linear combination is 0. But what we've seen is that's the same thing as ax equals 0. And we already showed that that means x is 0. So this equation only is satisfied if these are all 0. There's no way to combine the first 2 columns with the third, for example. And therefore, the set A1, A2, A3 is a linearly independent set of vectors. Okay. The columns do not span R4. Sorry, R4. We're in 4-dimensional space. Columns are in 4-dimensional space. But they are linearly independent, which means that the span really is 3-dimensional because they don't sort of there's no redundancy. We talked about that, right? So remember the column space of A, you just read about this, that's defined to be, it's by definition the span of A1, A2, and A3. And so we could say something like, knowing that the columns are linearly independent, we can say that the dimension of the column space is 3. So the column space, the span of the columns, is some 3-dimensional subspace of R4. Okay. And then for the null space is the set of homogeneous solutions, right? And so this sort of connects back to the whole thing where it's what we just said here, where we looked at ax equals 0 and we said, no, that's only the 0 vector. So, so we know the null space is just the 0 vector. We know the column space is some three-dimensional subspace of four-dimensional space. Okay. So that's the column perspective. And then the third, you can pause and go back over this stuff if you need to, but the third perspective is the transformation perspective. And let's just look at this for a second. So the whole idea is that if we take the matrix, we can use it to define a linear transformation. Basically, T of x equals AX. Oh my God, that's not what I wanted to do. And if we write that out really explicitly, here's x, right? This is A. There's x again. So that's A times x. And if we literally do the matrix multiplication out, we get this, right? So that's what the transformation is doing. It's basically you're plugging in, this lives in three-dimensional space. And then whatever numbers you plug in for x1, x2, x3, they go into this formula and you get a y1, y2, y3, y4. So the inputs are the x's, the outputs are the y's. Notice that this is really just the left-hand side of the system of equations, right? It's really just kind of, this really is like ax equals y up here. But it's just this different way to think of it now, where we're thinking of this thing as a transformation where we're plugging in vectors in R3 and it's spitting out vectors in R4. And so we get, remember, that's just how we write such a transformation. The domain is R3, the codomain is R4. Okay, so that's just what the matrix gives us. It gives us a transformation. If we want to specifically think about the vector B again, well, that's this equation ax equals b, and now we would write that as tx equals b. And this is really saying, like, is there an input x that outputs the specific vector b? Is there an input x such that t of x equals b, right? That's really what this is asking. But it's the same thing. It's the same thing we saw before. We've already solved this in both the row and the column perspective. It really comes down to the reducing the reduced echelon form. And we saw x1 equals 2, x2 equals 1, and x3 is -1. And so those numbers go into here. And so yeah, if we plug in the vector 2, 1, -1 into the transformation, it outputs 1, 5, 7, 5, which is our vector b. And yeah, that means b is in the image of t. Right this way, the image of t, or sometimes we abbreviate it IMT. And so remember, the image is like the range. It's the set of things that actually get output by the transformation, and b is such a vector. Okay, so so that output does have an input, but if we take c as our potential output, if we change it to 1, 6, 7, 5, then we've seen this has no solution, so c is not in the image. Okay, so what does that tell us about t? Well, it's definitely not onto, right? Because onto is, remember what we said, onto has to do with whether the image is the entire codomain. And yeah, since C is not in the image, that means that the image of T is not all of R4. And in fact, what I'm trying to put on the rug here, and what I'm going to come back and talk about in a second, is that really the image is the same as the column space. because they're both the same thing. They're both basically saying what are all the possible four-dimensional vectors you can make out of x1, x2, x3 in this matrix A, or x1, x2, x3 in the columns A1, the column vectors A1, A2, and A3. So this really is the column space of A really is the image of T. Okay, so those are the same thing, and that's why we're getting the same answer, that it's not all of R4, that the image is not all of R4. So that answer is on to, is it 1-to-1? Well, 1-to-1, you'll remember, had to do with saying, what if we had two different vectors inputs that gave the same output, right? And if you remember the argument we gave a while back, we could actually use the linearity of the transformation to say that would mean we could actually subtract the T of x2 to the other side and then sort of factor the T out in the sense of like the T distributes over addition and subtraction. And so we would see this is true, but that would mean A times x1 minus x2 equals 0, because that's sort of the definition of what T does. Oh, I should be using the 0 vector here. But we just said there are no non-trivial homogeneous solutions. So this implies x1 equals x2, or x1 minus x2 equals 0, I should say. It's the only way. That's the only vector that we can multiply A by to get 0, which means x1 equals x2. And so that's the argument that yes, T is 1-to-1. And in fact, okay, so T is not onto, but it is 1-to-1. So not onto has to do with the fact that there's, not a pivot in every row. One-to-one has to do with the fact that there is a pivot in every column. And well, we already answered the image. The image is the column space. It's not all of R4. It's really just the span of the columns of A. There's this word kernel, which I'm not sure we've talked about yet, but it's funny how image is a synonym for column space. Kernel is going to end up being an image, a synonym for null space. So the kernel of a transformation, it's just a weird fancy terminology that comes from math. It's defined as the set of vectors such that T of x equals 0. But that's exactly the null space of A, which we said here is just the 0 vector. Okay. So that means that, so it turns out that 1-to-oneness, we sort of actually can see this, these are kind of connected, right? By this argument I just gave, by this argument here, that the kernel, so we'd say the kernel here is trivial. And that is equivalent to T being 1-to-1. So it turns out that T is 1-to-1 if and only if the kernel of T is trivial. So that's kind of nice. Okay, so I wrote a lot on here and it's a little bit of a mess, but you notice there's connections among all this stuff. We kind of answer the same question over and over again. And that's what I'm talking about. We're sort of combining the perspectives or connecting the perspectives. When we looked in the row perspective, we looked at the homogeneous solutions. We said it was possible to have no solutions. And that's kind of equivalent to the column space not being all of R4, because we could find augmented columns that didn't give us solutions. So like there was no way to, so there, there was no way to sort of solve that system of equations, which we changed to the column perspective. That was right here where we said C was not in the span of the columns. And so that was the column space not being all of R4. And that connects to the image not being all of R4. So, you can sort of translate things from one perspective to another. Very similarly, the fact that there were no non-trivial homogeneous solutions sort of ended up being equivalent to the fact that the column vectors of A were linearly independent, which was equivalent to the idea that the kernel is trivial here too, because it's the same as the null space. So it's really, you're just answering the same question in different languages. Okay. What I want you to do next is to move on. You have this access to this sheet. I would like you to do the same sort of analysis that we did, to go through, write out, and like, here's an example of a 2x3 matrix. Actually, all I did was cut the last 2 rows off of the previous example. So I made it from a 4x3 into a 2x3. And now there's going to be a pivot in every row, but not every column. And then that changes your answers to some of the questions above. So I left all this blank space here for you guys to go through. And I'll put this on the course worksheet, but to go through and actually do the same kind of analysis I just did and try to write out all the conclusions you can make in the row perspective, in the column perspective, in the transformation perspective. Then I have one for pivot in every row and every column, which here I just deleted the last row from the original example that we did. And you can go through the same analysis. So this is really, really what you to do in group work. And then, hey, look, a pivot neither in every row nor in every column. So these are the 4 cases, right? You either have a pivot in every row and every column, a pivot in every row but not every column, not a pivot in every row but a pivot in every column, or not a pivot in every row and not a pivot in every column. So they lead to interesting different conclusions. There kind of are the 4 main cases of what you would ever encounter in linear algebra, honestly. And so if you kind of go through this and actually, go through these 4 examples carefully, you've pretty much gotten the whole picture of everything that can possibly happen in any of these situations. So, all right, have fun with that.